Okay. So I want to give you a little bit of a background for this because I want you to understand. This won't take that long once you get rolling. So I want to make sure you understand the logic. And I'm going to show you some things that like you don't learn in the book, but that are things that exist in the real world. So here's my intro to the, what did I call this thing? The retaining wall. And I mentioned this going out the door last week or Tuesday. Let's see, how do I want to do this? I think I'll try to do this 3D. Let's do this upright. So let's say I've got this building. And so that's the four walls of a building. And then because it's a two-story house, I say, okay, cool, let's put some floor joists on that house so that I got something to stand on the second story. And of course, that's what we're standing on right now because we're on the third floor and there's like something we're standing on. So this is kind of how this happens. So you build the four walls and let's see, let's say this is 22 feet and this is 48 feet. So that's the size of our building. And so here's what I decided to do. So I'm going to put this beam on here because maybe the floor joists aren't strong enough to go all the way across that by themselves. And so I'm going to put this beam in here and that's going to carry a whole bunch of the floor. And so I don't know if this makes sense, but then the floor joist would come and kind of anchor into that beam. And so in the end, the beam is going to be holding a whole bunch of that floor kind of all by itself. Does that make sense? And so if the floor joists are all sitting on there like I'm showing them here, kind of going so they're all spaced along there and the entire floor is there. So the question is, if you think about people standing on that floor, so let's say there's a beam underneath this floor right through the middle right here. Well, does it make sense if I'm standing right here, the beam is taking my weight? But if I go over here, now, does it make sense kind of like that wall's getting my weight? And so that one of the issues here is something called tributary. And this is on your sheet and it's a huge part of all beam design. Basically, how much is attributed to that beam? Well, would you agree the beam is 22 feet long based on the dimensions that are sitting there. So it's 22 feet long, but what's its tributary? In other words, how much of that floor is the beam actually responsible for? Well, here's the concept. It's really simple. The concept is if I kind of divide it right there, does it make sense that all the weight that's kind of over here is actually attributed to the wall because I'm basically closer to the wall, whereas all the weight that's kind of right here, all the people, for instance, they'd be attributed to the beam. So that's kind of what I was getting at earlier. So as it turns out, that's just kind of split. So since that's 48 feet, then would this distance right here be 24 feet? And so basically this 12 feet everything that's inside that 12 feet is sitting on the beam and everything that's on the other 12 feet is actually sitting on the wall over here. Do you understand that? Does that make sense? Are you seeing that? And so for that reason, basically the beam would be carrying this 12 feet and it'd also be carrying that 12 feet over there for a total of 24 feet of tributary. So the two things you got to know about a beam is basically how long is it? The longer it is, the weaker it's going to be. It's going to want to bend more and going to want to break more. And then how much of the floor is attributed to it. Now it turns out floor systems in a house are 40 pounds per square foot of live load, and they are 10 pounds per square foot dead load. So a total of 50. Now remember, the 40 comes and goes, but like when none of us are in here, this floor is holding weight because it has carpet, it has a subfloor underneath it, it has the floor joists themselves, and so those are 10 pounds a square foot, and that's just there all the time. That's why it's called dead load. And then 40 pounds per square foot comes and goes. The room fills up with people, then people leave. This is not a roof, so we don't get snow. The only thing that would ever happen in here is people. Now, could you do something in here that would break this? Could you like bring a pool in here and like fill the pool up in the middle and then crashes through the first floor? Absolutely. So there are weird things you can put. I've designed a number of decks and people are like, I want to put a hot tub over here. That's a game changer. If you want to put a hot tub on there, water weighs like 8.5 pounds a gallon. And hot tubs are, quite a few gallons. It doesn't take that big of a hot tub, but a lot of gallons, and it's a huge ton of weight. So it's like, if I don't know that, then that's not good. Like you got to figure that out ahead of time. So that's not a distributed load. So notice that 40 pounds per square foot, that's literally every square foot is 40 pounds. Now you might think, wait a second, don't you weigh 180 and aren't you standing on 1 square foot? The answer to that is, yeah, that's exactly right. However, it makes sense. People can't get super close to me. So, in the end, I'm still taking up like maybe 4 square feet. So that kind of spreads that out a little bit. But notice that number is a bit arbitrary. Like why 40? Why not 45? Why not 36? Like where did that come from? That came from people doing statistics on, what does a room full of people look like? Now, could we crowd in here like sardines and, fill this up? And then would the floor break? The answer is it won't break, but it'll deflect so much that downstairs people would kind of notice it, and the sheetrock would crack and things like that would happen. Or if we, all sort of kind of go, okay, jump, 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 and we're all packed in here together, like that would impact it like that. Maybe this wouldn't be designed for that. Like 40 pounds might not do it then. And so all I really want you to understand is this concept of tributary. How much of that is sitting on here? So let's just look at another example then. In the case of a roof. So here's a roof. Let's say this house is 36 feet wide. And so out here, I've got, snow coming down on the roof and so forth. A roof for at least a house is 15 pounds dead load and 25 pounds live. And why do you think why would the roof have more dead load than the floor? What is the roof carrying that's dead that weighs more? That's live load because it comes and goes. Yeah, like roof shingles are made out of rocks and stuff, or maybe even tile, like a tile roof or something. There's just more stuff up there. It weighs more than carpet. What you put on your roof usually weighs more than carpet. So that's a larger dead load. And then live load, interestingly, it's less. And you think, well, wait a minute, snow, but people weigh more per square foot than snow does. It depends on what area you're in. The other thing I would say is that 25 live load, that's because we live here. And you notice the other day it snowed like a foot. We never get that. It snowed like a foot. Well, that's why right there. But if we lived in Colorado, would it be 25 pounds a square foot? No, it would not. It's way more. And I've drawn some stuff that was up by Callahan's up on the top of the pass going over, and it was like 90 pounds a square foot. And again, like if I screwed that up, that'd not be good. Like that's a game changer. There's a website you actually go to that, and you type in the longitude, latitude coordinates, and engineers and trust companies and people like me that draw plans can all go there, and then that's where you get that number. So the point is, the load in the real world is not some arrow aiming at a drawing of a beam like it is in your book. It's like you got to come up with that yourself. There's never going to be an arrow aiming at something like your book assignment. You have to go determine the load yourself based on what the standards are in that particular area, and the concept of live and dead load need to make sense. Now, from my perspective, this still adds up to 40, and I don't really care because I have to think of it as loaded, right? So it's, as far as I'm concerned, it's really 40. So So I have this wall over here. And so let's say we took out this wall because this is somebody's porch and we put a beam right there. So that chunk of the house is actually not sitting on a wall, it's sitting on a beam. Well, how much of the roof is attributable? That's why it's tributary. How much of that roof do you attribute then to that beam? Does it make sense to you that, this snow over here is going to land on that wall? So that snow on that side is not attributable to the beam. So again, it's cut in half. This building is 36 feet wide. Everything that's over here on this half is going to sit on that beam, and everything that's on the other half is going to sit on whatever's on the other side of the house. So that means this would have 18 feet of tributary. Now, if the building itself was 36 feet wide, and then this was as it often is, a 1 foot overhang, does it make sense you'd have 18 feet plus the overhang? So that'd actually be 19 feet of tributary then? Does that make sense? So then here's kind of the calculation that I would make. So remember, these are pounds per square foot numbers. So since this is 40 pounds per square foot, then I would say times 19. Well, wait, it's 19 feet, isn't it? It's not 19 square feet. But what we're considering is a 1 foot stripe of the house. Basically, how much does every foot of the beam have to carry? So in a sense, you got to picture the roof is kind of being 3D like this. And so 1 foot slice of the beam up there, that'd be a 1 foot by 19 foot slice. So that is actually 19 square feet. Does it make sense then? Those units would cancel, and that would tell me how many pounds are actually sitting on that beam. So if it was 20, that'd be 800 pounds. So that I have 800 pounds attributable to it. And that's one of the things I can look up. I don't think I have this easy for me to see, but I've showed you quickly some of the beam charts, and one of them will say, how many pounds per lineal foot can this beam hold? Well, I need 800, and so I need some beam that can hold more than 800. Okay, so that's a rough introduction. Now let's take a look at our problem. So you don't have this, but this is the problem when you put soil against the retaining wall. If you push against it, then it wants to tip up like that. Well, that's moment, right? This thing wants to tip over. Now, if those forces are pushing on that wall, does it make sense? The other thing it wants to do besides tip like this is just flat slide. And isn't that what we've been studying lately? That's why this project lives here. Isn't there two things that can happen to this wall? It can translate, it can move. And in our case, it would just move along the X direction. It's not going to lift up or go down, but it will slide in the X direction. Or if there's enough friction, or in the case of see if I drew it this way. Sometimes in the case of a real house, if this is the outside dirt and this is the house, there'll be like a concrete floor poured here. And so it'll like hit against that floor. And so it won't be able to slide this way. But if you just set it on the dirt, it darn well could slide along the dirt. So maybe I have to drill some holes in it and run some concrete down into the ground so it can't slide. So I got to make sure it doesn't slide. If it doesn't slide though, it still can kind of do this over time, right? And I said over time because it probably won't do it immediately, but over time it can start bending like this. And so that's what I got to keep happening. That's called overturning moment. Do you notice those arrows get longer and longer and longer? Why would that be? The further down you go, the more dirt there is pushing. And so this is the concept behind scuba diving. If you swim underwater, there's more and more pressure the more you go down because you basically have more and more water sitting on top of your head. And one of my great childhood memories is deciding I was going to put my mouth on a hose and I was going to swim to the bottom and just hang out down there because now I got a hose and it goes to the top and I can just breathe. If you haven't tried that, you gotta like live a little more. It seems like that would work great, but it doesn't work at all because there's so much water on your chest, you're not strong enough to go and inhale. So I had to swim back to the top.
But as a kid, you don't understand. You're like, I can't take a breath in.
What's wrong? It's a weird thing. It's like you're trying to breathe in and you just can't. It's not like you can tell. It's not like it feels like, oh, I can't lift this. You just can't. It just won't work. Like, how come I can't do that? So, and I was only 8 feet down in the water, but remember I said water weighs weighs like 8.5 pounds a gallon. So if you're in 8 feet of water, what is that, like 70 pounds? It's like having roughly 245 sitting on your chest and like, oh, I'll just lift those up. So you can imagine if you go down even further, it's even worse. So we won't talk about that now, but see how that's triangular loading right there. That's not one arrow pointing at it, it's lots of arrows. And that's something we got to do later in this class, is figure out how much would that really be. Just out of interest for now, notice it says 120 pounds per cubic foot. That's how much dirt weighs. That's the accepted value for what dirt weighs. Notice it's cubic feet because that'd be a volume, not an area. And then 40 pounds per square foot effective fluid pressure. So if you have actual water is really good at taking downward pressure and converting it to like pushing sideways. But dirt has a lot of friction in it. So dirt wants to go down. It's not going to push sideways. And so you get only like a third of the amount of force sideways as a result of it being dirt. But the point is, there's weight back there for now. And if it does tip, notice that there's a toe and a heel, and that's actually the word for it, which is kind of nice because it's going to make sense, right? And so it all comes down to that thing wants to do that. And that's what it wants to do. And so if you just build it like that picture shows, it's not going to work because there's nothing keeping that from happening. But take a look at this picture over here. There's the foundation with its dirt behind it over here. But notice there's a whole bunch of stuff keeping that from happening. This is called resisting moment. And again, that's the language of engineering. That should mean something to you now. Like, oh, I know what moment means. That means rotation. And we need to resist that. Can you see that the weight of the roof up here, that has weight, the weight of the wall, that has weight, the weight of the floor, because this is a 2-story house, has weight, just the weight of the concrete wall itself. Like, can you picture in this, like that weighs a lot. Like that's not, you're not going to walk up and push that over. Concrete weighs a lot. It weighs, well, it says in here, 150 pounds per cubic foot, 150 pounds for 1 cubic foot. Like you can't even lift that. So you're not going to walk up and just push this over yourself. So even with nothing else but just its concrete, it doesn't want to do that. Does that make sense? It's going to take a lot of dirt just to kind of get that to tip. So we got all kinds of stuff on this house. Even this dirt right here is actually parked on the back, isn't it? Like it has to lift that dirt, doesn't it? And it doesn't, that's helping. And then just the weight of this thing alone, I mean, here's the footing. It's like, you know, I have to work to lift that up in the air, even if there's nothing else pushing down. Now that I'm pushing, it really doesn't want to lift. So it's like, look at all that stuff that's resisting that. Well, this is what you do as an engineer. You are the person that specs out that I want this wall to be 8 inches wide. The most important calculation on this is how big is this piece of the concrete and how big is this piece? Because that's how you control the D in the force times distance. You get to make that distance right here as long as you need it to be so that it's really hard for it to lift that. Does that make sense? So notice I'm telling you all kinds of things here. I say, okay, roof, what is that? You have 12 feet of tributary and then 25 pounds per square foot live load and 15 per square foot of dead load. So that's enough for you to tell what that roof actually will weigh. And we are considering this as a 1 foot, you might add this to your note. This is a 1 foot slice of this house. Basically, if we can get 1 foot to behave correctly, then that means all of the feet will behave correctly. Do you see what I'm saying? And then the wall. How come the wall has 8 pounds per square foot dead load and no live load? Yeah, it doesn't snow on walls. You don't walk on them. Like there's no other, it's only dead. I mean, you can hang a picture on it, but that's kind of like a fly, right? There's nothing changes. That's why a wall's only dead load. So that's 8 pounds per square foot of dead load. Notice you need to know how tall it is because the taller wall is going to weigh more. So you have to think of that as a 9 foot tall, 1 foot wide slice of wall. And then it's 8 pounds per square foot. So you can actually come up with how much does that wall weigh. And then let's take a look at this floor. Just like the roof, it's got 12 feet of tributary. So maybe this is like a 24 foot wide house. That's why it's 12 feet. And then I gave you the same floor load numbers down there, 40 and 10. And then you've got this concrete. And notice I told you the dimensions, it's 8 inches. It's 8 inches here and it's 8 feet tall. So you know the dimensions of that by 1 foot wide. Notice the units are problematic because that's 8 inches, not 8 feet. So you can't treat 8 like 8. Those are two different 8s. And then you've got this footing over here. It also is made of concrete. And you know its dimensions. Notice this 8 up here would be this distance here. So you have 8 inches and 16 inches and 28 inches. So that's, you know, altogether whatever the heck that is. And then lastly, you've got soil. As I told you a second ago, it's 120 pounds per cubic foot, and that's pushing down over here. And so those are all the things trying to push back, since, and this is very important that you understand this, you should add this to your sheet. That's the tipping point right there. So that's where our distances are going to be determined from. So the toe or the tipping point. Everything, all of these forces are to the left of that. So what I want you to calculate then is, what is the resisting moment? Like how much force times distance is there pushing back there? And then later on, we'll see, okay, now how much is the dirt going to try to tip it? And we need to make sure the resisting moment is bigger than the tipping moment. And if it is, we can guarantee, okay, that's not going to tip over. And you can appreciate in the real world, like this is someone's house that fell down. That's like a $1 million mistake right there. You can't do that. One of those in your lifetime is all of the money you ever make. You can't get this wrong. So then I have a few abbreviations up here at the top. I've been saying them out loud, but just so you know what those are. Now, check this out. Why did I outline that in black? Calculate the resisting moment for the retaining wall, dead load only. Why did I say dead load only?
So we have one answer of like the basic, we're not taking into account snow or people, we're just like, how can we?
Why are we doing that though? Just because we want to?
Oh, this is for the wall, because you're not gonna have a live load underground, right? It's, I mean, maybe if you add more.
Well, these are live loads, like it snows up here and so, hey, look, it snowed on our roof. Hey, look, people, water beds.
Because that's not changing the moment, is it?
Yeah.
Because the more live load you have, the more it's gonna be pushing down on it, so it won't want to tip. So the dead load is like the least amount of force required to keep it tipping.
Exactly. Can't live load go away? Like, oh, snow's gone. Well, then you don't have the snow helping you hold it down now. Like you can't count on the snow being there, right? What about people? Oh, they're gone, they're at work. You can't count on live load because it might not be there. Like you need, if everybody leaves, you can't have the house tip over. And so you got to stay home. You got to stay home and like hang out over here. You got live load doesn't exist. Like it comes and goes. That's why it's called live load. So we can't calculate off of live load. Again, that'd be an honest but life-changing mistake, right? So this is, again, this is real. So even though there was live and dead, I can't count on live loads here. I can only work with dead loads. Now, I gave you a giant drawing. This is the actual drawing. And by the way, this is exactly a house that I had engineering done on. If I had time, I would show it to you. But I took this problem directly from what my friend sent me. And notice, by the way, do you see how he has a basement slab drawn in there? Does it make sense? That's going to keep this thing from sliding. So that's taken care of, if you will, because there's something pushing back against that. This isn't just sitting on the ground. For a long time, he used to tell me, is there a slab down there? And I was always like, why do you care? It's like, why do you need to know that? And now I'm like, oh, that totally makes sense because this thing will slide because we got a bunch of dirt back here pushing on the back of this. And notice sort of the toe side of this is really big, whereas the heel side is kind of small. See, that's the decision he makes. He's the nerd, like nobody else understands that. The people that go out to pour the concrete, they just look at these dimensions and pour what the engineer said. The builder doesn't understand. None of us understand it. Only the engineer is the one that makes the calculations you're making and understands them, and there's nobody they can even tell. They just make the calculation and stamp and says, this will be great. And everybody goes, okay, and they just do whatever the person said. So these dimensions are also in the drawing above, but notice in the end, this footing was 4 feet 4 inches long. That's huge. I mean, that's like this wide. That's a really giant footing. And what I want you to see as you're making these calculations is why is it so important that that toe is so big? Does it make sense that that's creating the distance you need? If you look back at this drawing back here, isn't all of this weight kind of back here? And so isn't the length of this, doesn't that cause that toe to be way out in front of you? And so that makes the D really large. And since moment is force times the distance, if I double that distance, I'm going to get double the amount of moment just by making that toe part of that footing a little bit longer. Does that make sense? Now, I may give you something about this for an extra credit, because one of the things I asked him is, how do you know to make this toe 2'4", and then you go make all the calculations we make? What if it's like, oh, well, that's too small. Now you got to make it longer and go do them all again. Or if it's way too big and it's like, oh, that's way bigger than we need. Oh, let's go make it smaller and calculate it again. So one of my questions to him is, how do you know that? And his answer to me was, I just kind of have experience, because I noticed when I calculated his, it was way too big. And I was like, God, you're spending people's money and time when you're doing that. And I get, like, from his perspective, he goes out of business and gets sued if he gets it wrong. So he's definitely going to make it bigger than it needs to be to make sure he never gets any phone calls, which he's right to do. But where's the line between like spending people's money and, and people kind of hate engineers for that reason. They'll spec out a bunch of expensive stuff and and it obviously costs money to hire you. So they don't want to use engineers if they don't have to. So I may give you an extra credit and actually have you recalculate what's the minimum this could be. But we'll talk about that later. Okay, so I made this awesome chart, which I actually made for my calculus class a little while ago. And so obviously to get the moment, this, I don't need to write this down, that moment is force times distance. So don't you need to know the force of the roof and the distance that weight is? Now, the only last thing that we have to talk about before I can shut up and let you think is, I don't think I said anything about this on here, but let's just consider this wall, for instance. Well, this wall is apparently like 8 inches wide. Where should I put all of that weight? Let's say the wall weighs 100 pounds. Where is that 100 pounds? Is it here? Is it here? Or is it like right in the middle? And generally speaking, that's the answer, is right in the middle. So let's do that for these calculations. Now, that can be sometimes screwed up. Like, see this roof rafter up here? So if this rafter weighed 1,000 pounds, notice how it's attached to that wall up there. You see it's actually kind of on the outside edge. And so there's a little bit of tweak to this. I guess you might say the roof load, the wall load actually might be here, but the roof load actually might be there, right on the outside, because of how that actually goes together up there, since that just sits on the outside edge of the wall. So the point is, all of these things, like the floor joist, where are we going to consider its weight to be? If this is 1,000 pounds, where's that weight? Let's just put it in the middle of the wall. Yeah. So see, the important thing is going to be to say, okay, well, if the wall's weight is right here, then what's its distance? Well, then that's its distance. So the distance is huge. The distance is more important than the weight. So that's exactly right, because that's in the middle, that'd be 4 inches. And this entire chunk right here, maybe it weighs 1,000 pounds, but where is its weight? Well, it's right in the center. Isn't that what we've been learning in this class? You can replace all of the weight with just one arrow. Maybe it weighs 1,000 pounds, but it acts as a particle. It acts right in the center of that thing. And of course, that'd be important, because then that's how I determine the distance. And then the other problem is, all of these measurements are in feet, right? So in a sense, anything that says inches, you're going to have to convert it to feet. Otherwise, your calculations aren't going to work. So think about that. So work together if you want to, or do it yourself, but kind of check don't just answer them all and then go, oh, I'm wrong. Like, compare this to your neighbor. So obviously I get a force and I get a distance, and I can multiply them and I get the moment in foot-pounds. And as soon as I add all of those up, then I'll have the total resisting moment. How much desire does the house have to keep that thing from tipping over? And also, you may not have had a lot of exposure to reading plans, so this is kind of a good opportunity to learn how to read dimensions, make sure you understand where the measurements start and stop. So ask me those kinds of questions too.
So then we said 1 foot slice of house. What's that go over?
It's for everything. So we're literally thinking of every single thing we see as 1 foot into the paper, so to speak. We're figuring out 1 foot. And if we figure out that 1 foot, then the next foot and the next foot and the next foot will all be the same.